In this video, I want to take a look at proving divisibility results. So this is the second video here in our chapter on proof by induction. And all we're looking to do in this video is take an expression such as 4 to the power of n minus 1 and show that this is divisible by 3 for all positive integers n using proof by induction. And how do we do that? Well, because it's a proof by induction, like we saw in the previous video, we just follow the same 4 steps here. So we start with the basis step, we then move on to the assumption step, we then move on to the inductive step, and once all of that is complete, we then have our conclusion to finish the proof by induction. Okay, and the same is true for divisibility results. So nothing different, we follow the same 4 steps. So let's take a look at this first example here then. We want to prove by induction that for all positive integers n, 4 to the power of n minus 1 is divisible by 3. So the very first thing that I'm going to do here before I even start the proof by induction is define 4 to the power of n minus 1 as a function. So here I'm going to define this then as f of n is equal to 4 to the power of n minus 1. Okay. So this is a proof by induction. So we start with the first step then in our proof by induction, which is the basis step. So we have the basis step here. So for the basis step here, I'm just going to let n equal 1. Okay, so it's our starting point here. So I let n equal 1 here, what would I get? Well, what I get then is f of 1. So f of 1 here is equal to 4 to the power of 1 minus 1. Okay, 4 to the power of 1 is 4, minus 1 gives us 3, and clearly 3 is divisible by 3. Okay, so nice and straightforward there. So all we need to say here then is that f of n is divisible by 3. This is divisible by 3 when n equals 1. Okay. So nice and straightforward there to get us started. So that's the basis step complete. So now we move on to the assumption step. So now for the assumption here. What we're going to do now is assume this is true for n equals k. So we assume this is true for n equals k. So assume true for n equals k there. So if this is true for n equals k, what I'm saying here then, let me write this down in full, is that f of k is equal to 4 power k minus 1. And we're saying this here then is divisible by 3. Okay. So this here is divisible by 3. Okay. So that's the assumption step complete. So now we move on to the inductive step here. So we'll do that underneath. So now for the inductive step here, we let n equal k plus 1. Okay, so n equals k plus 1 now. So if n is equal to k plus 1, what would we get here then? Well, substituting n equals k plus 1 then, we get f of k plus 1. So f of k plus 1, and that is equal to 4 to the power of k plus 1 minus 1. So 4 to the power of k plus 1 minus 1 there. Okay, and that is f of k plus 1. So that's just f of k plus 1. What we need to do now is show that this is also true for n equals k plus 1. So that's my inductive step. But how do we do that just using this information here? Well, a really clever way of doing this is to set up a difference here. Okay. So if I consider the difference here then of f of k plus 1 and f of k. So what I've got here then is f of k plus 1 minus f of k. And you might be wondering why we set up this difference here. And the reason why is because f of k, we derived that essentially using the assumption step. So we assumed it was true for n equals k. So then we got f of k being equal to 4 to the power of k minus 1. And we said that that was divisible by 3. So if we assume it's true for n equals k, we're saying that this here is divisible by 3. Okay. So once I set up this difference here then, I've got f of k plus 1. So if I've got f of k plus 1, and I subtract f of k, which we know is divisible by 3, using the assumption step here, if my result here then is also divisible by 3, if I can show that that's divisible by 3, then what that would mean then is f of k plus 1 is also divisible by 3. Okay, so that's what we're looking to show now. Okay, now we have expressions here for f of k plus 1 and f of k, so let me just replace those then. So f of k plus 1, do these in square brackets here just to make sure it's clear. I've got 4 power of k plus 1 minus 1. So that's my first square bracket there. This one is a little bit unneat. Let me just redo that so it's a little bit neater. So setting this up here in square brackets like so. We then minus f of k here. So f of k here then, that is 4 to the power of k minus 1. So 4 to the power of k minus 1. There we have it. So that's f of k plus 1 minus f of k. So what I'm looking to do then, like I said here, is show that this result then, so this difference here is also divisible by 3. Okay. Well, the first thing that I notice here is minus 1 minus minus 1. Well, they'll cancel because that's the same as minus 1 plus 1. So they'll cancel like so. And what I get left here then with is 4 to the power of k plus 1. So 4 to the power of k plus 1 minus 4 to the power of k. Okay. So what I need to do now is use the rules of indices here. Okay, because what we're looking to do here is show that this is divisible by 3. So what I notice here then is 4 to the power of k plus 1, using the rules of indices then, we can write this as a product. So this would be 4 lots of 4 to the k. And then we minus 4 to the k here, like so. So now if I've got 4 lots of 4 to the k and I minus 4 to the k, what I've got here then is 3 lots of 4 to the k. Okay. And clearly, this here must be divisible by 3 because it's 3 lots of 4 to the k. Okay. So we were looking to show this is true for n equals k plus 1. So now what I can see here then is f of k plus 1. Going back to this expression here then, that would be 3 lots of 4 to the k plus f of k. Okay, adding f of k to both sides here. So I get f of k. So f of k plus 3 lots of 4 to the k. Okay. And we just think about this for a moment. This full result now must clearly be divisible by 3 because we know that f of k is divisible by 3 using our assumption here. And this part here then must also be divisible by 3 because it's 3 lots of 4 to the k. Okay, so this part here is divisible by 3. This part here is also divisible by 3. So the full result then for f of k plus 1 must also be divisible by 3. So there we have it. So that's our inductive step complete then. So what I'll need to do now is write the conclusion. And we've run out of room here, so let me just clear the screen. So now for the conclusion here. So now for my conclusion here, what I say then is based on the inductive step is that f of m is divisible by 3. So f of n is divisible by 3 when n equals k plus 1. Okay. And if this is true for n equals k, it must also be true for n equals k plus 1. So let's just write that down as well. And if true for n equals k, then this must also be true for n equals k plus 1. Okay. And because we saw it was true for n equals 1 with the basis step, then this must be true for all n that belong to the positive integers. Okay. Let's just write that down to finish with here, and true for n equals 1. And this must be true for all n that belongs to the positive integers. Okay. And there we have it. So that's the solution there to the first question. Taking a look then at one more example here, we've got the function f of n, which is equal to 7 to the power of n minus 3 to the power of n. So this question structure is slightly different. So rather than it being one full question, this is now broken down into two individual parts. So for the first part here, I want to show that f of k plus 1 is equal to 3 lots of f of k plus 4 lots of 7 to the power of k. And the reason why it's structured like this is because the actual proof by induction involved here in part B is slightly more challenging than, say, the previous example. So basically the inductive step here, that's what we're given in part A. Okay, so it's just there to help us a little bit as we work through this question. So let's begin with part A then. So what I can see straight away with part A is this result for f of k plus 1 involves f of k. I'm going to start by quickly defining f of k. So f of k, that would be 7 to the power of k minus 3 to the power of k. Okay. So now for f of k plus 1, let's see what we obtain here. Well, that would be 7 to the power of k plus 1 minus 3 to the power of k plus 1. So 7 to the power of k plus 1 minus 3 to the power of k plus 1. Okay. So what we need to do now is go from this line here to this result here. And there's clearly a bit of work in between here, so let's get started with that. So what I notice here then is 7 to the power of k plus 1 and 3 to the power of k plus 1. I can use the laws of indices here to basically write these results as a product. So here I'm going to get 7 lots of 7 to the k, 7 to the power of k here. Then have minus 3 lots of 3 to the k. So again, just using the laws of indices here. So that's my next line of work in there. Now, the next line here is probably the trickiest part to this full proof by induction. And this is essentially what we call splitting. So what I'm going to do now is take this here and be really quite clever in how I split this up. So what I'm looking to do is get 3 lots of f of k plus 4 lots of 7 to the power of k. So what I'm going to do then is essentially factor out a 3 here. So I'm factoring out a 3, like so. I'm going to write this in as 3 lots of 7 to the power of k. And I'm going to minus 3 to the power of k. And notice here, this 7 to the power of k minus 3 to the power of k, this is actually f of k. Okay, so what I've actually got here then is 3 lots of f of k. But what I need now is to basically get something that's equivalent to this line. So what I've got here then is 3 lots of 7 to the power of k. And I've got minus 3 lots of 3 to the k. So this bit's complete. That's equivalent. But here, I'm essentially missing 4 lots of 7 to the k. So I now need to add that back on to make sure that this line is equal to this line. Okay, so hopefully that's clear what I've done there by splitting this up. So now we add 4 lots of 7 to the k. Okay, so again, just explaining that step there, because I think it's quite tricky to see what's actually happened here. So basically, I'll split this up now into 2 parts. So taking out this 3 here, I get 3 lots of 7 to the power of k minus 3 lots, minus 3 to the power of k. Okay. If you think about expanding this out for a moment, I'd get 3 lots of 7 to the k minus 3 lots of 3 to the k. But I'm still missing another 4 lots there of 7 to the k to take me back to this 7 lots of 7 to the k. Okay, so hopefully that's clear what we've actually done there. Like I said, it can be quite tricky to see what's actually happening the first time you see this. But then clearly what I'm going to get here then, well, this here, that's f of k. So I get 3 lots of f of k. And I get 4 lots of 7 to the power of k. Okay. like so. Okay, and there we have it. So that's as required. So that's for f of k plus 1. Okay, as required. So that's part A complete. And that is our inductive step. So that's what we've just done in part A. So we've completed the inductive step to our proof by induction. So now for part B, it's just actually asking us to complete the proof by induction. So remember, we go through the 4 steps here. So for the basis step then, we let n equal 1. So if we let n equal 1 here, what would we get? I'd get f of 1. So f of 1, that's 7 to the power of 1 minus 3 to the power of 1. So this gives me 7 minus 3. And that is equal to 4. And clearly, that is divisible by 4. 4 is clearly divisible by itself. So in that case then, what we're saying now is that f of n is divisible by 4. This is divisible by 4 when n equals 1. Okay? So that's the basis step complete there. So now if I just kind of split these off here. So now we move on to the assumption step here. So now for the assumption here, what we do now is we assume this is true for n equals k. We assume this is true for n equals k. So if I assume this is true for n equals k, then what I get here is this result. So therefore, f of k is equal to 7 to the power of k minus 3 to the power of k. And what I'm saying here then is this result is divisible by 4. Okay, so this is divisible by 4. My next step now, so my assumption step here is complete. We now have the inductive step here, but we've already completed the inductive step here. Okay, that was everything that we did here for part A. So I'm not going to repeat that. So all I'll say here is, as part A states. Okay, so we've completed the inductive step in part A. We don't need to worry about doing that again. So just going through the inductive step here, doing that for f of k plus 1, just splitting that up and getting this here then. So now you need to understand why the inductive step works here. Okay, so I've got f of k plus 1. And what I can see then is I get 3 lots of f of k, okay, plus 4 lots of 7 to the power of k. So why is this full expression here divisible by 4? So basically what I've said here now is f of k plus 1. This is divisible by 4. But why? Well, 4 lots of 7 to the k, that's clearly divisible by 4 because it's a multiple of 4. So that's, I think, quite obvious. F of k here, well, going back to the assumption now, we assume this was true for n equals k. So we've got f of k being equal to 7 to the power of k minus 3 to the power of k. And we said that this is divisible by 4. Okay, and that's what we're assuming. So if we're saying that this is divisible by 4, it doesn't matter what you times this by, okay? You could times it by 3, 2, 100, a million. It doesn't matter what you times it by. Because f of k here is divisible by 4, this product will also be divisible by 4, okay? And that's what we're going to basically show here. So this here is divisible by 4 because f of k is divisible by 4. So obviously, like I said, don't matter what you times it by. This here is a multiple of 4, so it will obviously be divisible by 4. So therefore, f of k plus 1 is also divisible by 4. And that's what we're going to state now in the conclusion here. So I'm going to clear the screen here just so I've got enough room for my conclusion. So now for the conclusion here, just to sort of summarize everything that we found here. So what we've shown there is that f of n is divisible by 4 when n equals k plus 1. So f of n is divisible by 4 when n equals k plus 1. Okay, so that's what we showed in part A to this question here. So if this is true for n equals k, so if true for n equals k, then this must also be true for n equals k plus 1. And this is true for n equals k plus 1. And because we showed it was true in the basis step then for n equals 1, so and true, and this was true for n equals 1, and we know this is true for all n that belongs to the positive integers. Okay, so and true for n equals 1, and this is true for all n that belongs to the positive integers. Okay, and there we have it. So that gives our conclusion there, and that gives the solution there to the second example, or the second question, and that brings the end of this video on proving divisibility results.